So the point to trying to identify acids and bases and clearly define them in part is to be able to predict the products for reactions. And so that means you have to be able to identify an acid and the base as your reactants and then decide how that reaction will proceed to form products. And I'd like to show you how to do that prediction piece next. Um, so, first, really quickly, I want to show just a few types of acids to help get you a little bit more familiar with what you're looking for. Um, because I believe that this is a gray area in chemistry, and oftentimes it's something where you decide through experimentation, but we have some patterns that we see again and again structurally. So first we have binary acids. Binary acids are just two things. It means it's a hydrogen atom bonded to something else, and that hydrogen atom is acidic. Perfect example of this is hydrochloric acid. And so we actually see with a lot of binary acids that they're going to be a hydrogen bonded, ah, sorry, a hydrogen bonded to a halogen. We might also see a hydrogen bonded to a larger molecule that has more atoms than that, like a hydrogen bonded to S and another hydrogen. The common ones, though, are hydrogen bonded to a halogen, like fluorine, chlorine, bromine, or iodine. Next, we have oxyacids. Oxyacids are always going to have this hydrogen bonded to an oxygen. So this means hydrogen bonded to an oxygen atom. And then oftentimes that oxygen atom is bonded to something else, like a nitrogen or a chlorine or a phosphorus or a sulfur. And sometimes there's even more oxygens inside the molecule as well, like we have here with HNO3. And the idea is that that hydrogen is in that hydrogen oxygen bond. It's very partially positive, and so it's easy for that bond to break and that hydrogen to become part of another molecule like a hydronium ion. Another kind of group that we'll see again and again and again are carboxylic acids. These are often called organic acids because they have carbon and oxygen in them. And so this looks exactly like the oxyacid. Same exact pattern. You're looking at a hydrogen bonded to an oxygen, but the trick is that the thing the oxygen is bonded to is always a carbon. So there's always that carbon right here bonded to the oxygen that's bonded to your acidic hydrogen. And so that's that important motif. And carboxylic acids also, or in particular, have this double bonded oxygen right here. And this is actually what we call a functional group in organic chemistry. And there's lots of functional groups when you're learning about how molecules tend to arrange themselves. But this is a pretty important one for organic chemistry. A lot of our weak acids are actually carboxylic acids. So let's look at Bronsted-Lowry acid-base reactions and talk about how we predict the products and what we have when these acids and bases are brought together. So, in a Bronsted-Lowry acid-base reaction, what we're going to see is that our original base, which is going to be that proton acceptor, is going to form a product that is itself an acid. And the acid, which was the proton donor, is going to form a product that is itself a base. And so, right, okay, so our acids become bases and our bases become acids. That's super confusing. So we are going to give our product acid and base a kind of different name. It's going to be the conjugate acid and the conjugate base to say, hey, it's the product of an acid base reaction, right? And so we call this, and this helps us predict the products, right? But we call these pairs conjugate pairs. And so uh, in the case of our ammonia, which we've already talked about as a Bronsted-Lowry base, we have it right here. Here's ammonia and H3. When it accepts a hydrogen, so this is going to be my reactant, and it forms this product, it'll be NH4 plus. Well, that NH4 plus, that is an acid. And so we're going to call it the conjugate acid of ammonia. Now, water can act as a base, or sorry, an acid. Water can act as an acid, can also act as a base, but that's like in a couple videos. So when it acts as an acid, it's going to donate a hydrogen, right? And so my reactant, water, is going to donate a hydrogen to a base like ammonia, And I'll be left with O and an H and a minus, so hydroxide ion. And that is a base. That's actually strong. It's a good base. And so what I have here is a product that is a base, and then we'll call it a conjugate base because it was formed from the acid. And so these conjugate acid base pairs that we're seeing here, the difference between them is just a hydrogen atom. And so to predict what the conjugate acid of something is, you just add H. And to predict what the conjugate base of something is, you just subtract an H. So that's the only difference. And that's why acid base reactions are really just a hydrogen atom moving from one molecule to another. It's just a hydrogen atom shifting around when we look at these Bronsted-Lowry acids and bases. So let's show this in an example. Let's go back to good old hydrochloric acid and sodium hydroxide, the like classic chemistry acid base reaction. So we've talked about hydrochloric acid is an acid. Great. So I've like got that labeled. And sodium hydroxide is a base. If I'm going to predict the products for this reaction, my acid is going to, I'll use a highlighter. My acid's going to donate a hydrogen right here to my base. Here's my base. And so this hydrogen literally transfers over to that lone pair on the oxygen. And I form, now I'm going to draw this out here, right? So this is my product water. Here's the hydroxide that is part of it, plus the hydrogen that was added to it. And so it's really just shifting that hydrogen over. And when it shifts, this acid becomes my conjugate base right here. And my base then, which accepts that hydrogen, is going to become the conjugate acid. Now it has the extra hydrogen. And my conjugate base shouldn't have, I should be missing a hydrogen. In this case, it has none, right? So let's apply it to something else. If you want to pause and try this on your own first, please do. So this is our other example reaction. And we have our acid, which is our sulfuric acid. And we have our ammonium, which is our base. And so I'm going to take one of these hydrogen atoms and put it onto my nitrogen. And so that's how this is going to work. And so what I do when I'm writing my products is that I write H2SO4 minus one hydrogen. So that gives me HSO4. And for my nitrogen, I write NH3 plus a hydrogen. So instead of NH3, it becomes NH3 plus one. So NH4 right there. And then I can label these as my conjugate acid and conjugate base. So my acid is going to produce a conjugate base. And my base will produce my conjugate acid. And I just shifted a hydrogen around.